Hi, it's Larry Greenblatt. Welcome back for part 2 of my What is PKI? And today we're going to take a real quick look at TLS and how TLS will employ, as we saw in our earlier video, symmetric encryption to encrypt data, hashing algorithms to check the integrity, and we use asymmetric algorithms, again, to do key exchange, to encrypt the keys, and to sign. Right? Now, something like RSA can do both. Elliptical curve, we're going to see though, actually, well, let's take a look at a TLS handshake. So in TLS, every application gets to configure the client. So this is how Microsoft Edge has decided to set up their crypto suites, they're called. That's a very testable term, by the way, if you're a CISSP candidate. So in this particular Edge, I just did this trace yesterday. They support a number of, again, symmetric encryption is going to be used for encrypting data. And you could use AES. These are a little confusing here. Those are for pre-established configurations. So let's just take a look at these ones right here. AES, AES and 256, a newer stream cipher I'll cover in my class. I do not cover here. AES again in 128 256. And here we see the old cipher block chaining, but today we know to use Gaussian counter mode, right? And that's all you pretty much see today. For hashing algorithms, no more MD5, right? Got to use at least an SHA 256, maybe a 384. There's still some old SHA. Oh, we should get rid of that. Just say no to that. That's already cracked, right? Collisions. And then for our key pairs, for where PKI comes in, particularly what you usually think of is the signing key, right? Now, RSA can be used for both key agreement and signing. When we use elliptical curve for key agreement in TLS, we use elliptical curve as a Diffie-Hellman key exchange, and that would be used to say agree on these AES keys. But for the signing of those hashes, elliptical curve is called well, there's a few different versions, but in this particular version, it's the digital signature algorithm, DSA. It's an Edwards curve for anybody's listening. And RSA can always be used to sign. So they'll be used to sign these hashes, right? So the client advertised the server, this is what I support, and the server picks something. And so way back to yesterday, yes, this was the ISC square. The ISC square decided we're going to use elliptical curve to agree on this AES key. But as far as their signing keys, I don't know why. I know Google's been using elliptical curve DSA, but they decided to use RSA, practice what they preach, to sign that hash. It's okay. Notice the client hello was when the client announced what it could do. The server hello is when the server said, we're going to do this, right? This is the suite we're going to use. Now, when the server does that, they're going to have to give you their public key, in this case, RSA, so that you can validate the signing of these hashes. And we know that they do that in the X.509 certificate. So let's take a look at that real quick here. And the certificate here, this is just Wireshark's display of how this certificate looks. But the subject is who the certificate's for. And this is our X.500 name. This is an X.509 certificate to validate that, right? That's the 500 name. And well, where did they get it? You can't print your own driver's license. It's not PGP or self-signing. No, the issuer is always a certificate authority, not registration authorities, right? It has to be a CA. But when we go to and get like the ISC squared, that's not the root. That's some intermediate, and we need to understand how that works, right? So when you get a certificate, you can look at, where's the certificate path? Where did it come from? Well, okay, so the ISC squared got it from DigiCert validation server. Well, who are they? And I looked at their cert. Where did you get your cert? Oh, well, we, the subject, were got by this CA, and that's the root. Now, we have some issues. Root CAs are self-signed. I don't know the right answer here. I know that it's pretty easy with like a cat video to get Larry's evil CA in there, so be careful. Now, here's the real root CA. In my class, we'll talk about how we could maybe fix this, maybe blockchain these certificate authorities. We also talk about why did Microsoft only show 77 of them, and I know there's close to 200, but that's for my class. I hope this helps you understand kind of though how TLS works. So when you see TLS questions, again, in my class, you don't have to be the cook. You want to be more like a waiter. right? Engineers are like cooks in a restaurant, but waiters have to be good with customers and know what's on the menu. In what step of a TLS handshake does a server specify the required hashing algorithm? We saw that in a server hello. No, it's not even a it's SYN. That's not it, right? That's a TCP handshake. No, it was the server hello. Which of the following should be is most likely to be the issuer of a certificate for a web server, not the OCSP responder? We sniff them out. We look, wow, it's so much better than doing CRLs in my class. Registration authorities can't issue. No, they can't do it. It has to be a CA, but it's probably not the root. It's probably an intermediate, right? Yeah, intermediates. And then that's why you look at your certificate chain. That was supposed to be highlighted there, right? So we can see where that came from. And then if a server selects the following cipher suite in their handshake, and I'll tell you if anybody has ever done any sniffing, this is Google. This is how Google's been doing things for like 12 years. So elliptical curve, Diffie-Hellman, oh, well, that's used to agree on the SHAK, yes, I'm sorry, the symmetric K. Elliptical curve as a digital signature algorithm, that's used to sign this hash. Right? So elliptical curve, Diffie-Hellman agrees on this, and then the signature. All right, so which algorithm be used to sign? Oh, that's the digital signature algorithm, BCDSA. Well, yeah. And now I'm working on part 3. I want to show you how email is encrypted, and regardless of whether you're using PGP, just to give you a quick heads up over here, I'm going to use Thunderbird and show you guys. But regardless of whether it's a PGP or S-MIME, the technology for end-to-end encryption is the same. And the point of all of this is to digital signatures give us authenticity, and you could also, well, they'll give us integrity, not repudiation, but you could also encrypt the message, and we'll see how we do that regardless of technology. And we'll even take a closer look at SMIME 4.0. All right, wouldn't be a commercial video if I didn't have a listing of my products. Please buy something and sign up, click like, make comments, blah, 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 all that stuff. All right, I hope you guys found this useful. Take care.